Hey TJ Machine Learning Club. So today we're going to be lecturing on real-world machine learning, or specifically going into more of like the coding aspect for machine learning applications, because I think now that we have a decent understanding of the, major machine learning models, we can kind of delve into how exactly we code it if you guys haven't tried out the competitions and you haven't been really experienced to coding, or you just maybe don't know Python yet and you kind of want to see if you can get interested. So just starting with the intro. So far in our club, we've covered all sorts of machine learning algorithms like decision trees, random forests, SVMs, neural networks. And I guess the real question is, how do data scientists today code them, and what are, the most common tools or packages that are used in data science and machine learning today? So I think starting just with, focusing on machine learning from more of like a organized approach. We always start every machine learning project, with we need some sort of setup, before we can begin. If you guys haven't used, machine learning before, or haven't exactly tried coding with Python or different libraries. So normally, when you get some sort of machine learning problem, what you see first is the data, right? You're using this data, using some sort of features, whatever these features can be. They can be images, they can be certain values, like we've done in the past with SVMs and decision trees. And once you have these values of data, there's always a way to help you visualize this data using things like Excel, which like we probably use Google Sheets, Excel to help just visualize, see trends in the data that our model could also kind of help see. But I think in Python, there's a lot of tools for data visualization that can really help when you're getting just first started, like Matplotlib or Seaborn. Like for example, these images on the right, different images using Matplotlib and Seaborn, they help you as in Python itself visualize these charts and data. And a lot of the times, making these charts on Python itself will run much faster than if you, for example, try to make some sort of chart of 50, 60,000 lines of data in Excel. That will go much slower than if you were to just use Python itself with some data frames, pandas or NumPy. So if you guys haven't introduced, pandas and NumPy are kind of some major data science kind of libraries that help you organize data, create arrays, data frames, or series, and they're often used in machine learning. So a lot of times, before we start machine learning, these projects or so, there's a lot of different packages you need. For example, like these matplotlibs, you might need to use Jupyter Notebooks, Keras, scikit-learn, TensorFlow, things like that. So kind of one of these ways to get these packages is through Conda, which is an open source Python package manager designed for data scientists. And one way that actually you can install Conda is through Anaconda, which you might have heard before, where you kind of bundle all these packages and all these things together. And I guess like Conda can kind of be thought of as similar to pip. If you guys have used pip before to install Python libraries, where you say, pip install, NumPy or something like that. I think the main difference is a lot of data scientists today try to use Conda for their, machine learning approaches or data science coding over pip, because it helps group these different packages installations into separate environments, and this kind of helps prevent conflicts and create everything a little bit more organized. Another more efficient way to install Conda would be through Miniconda, which doesn't install, everything like these 150 plus packages. And this will help you, choose what packages to install. If you're a little bit more concerned about what's going on and what you're installing, that would be another approach for you to use. But I think with Anaconda, there also comes some things like Anaconda Navigator, which I think we use at the AI course at TJ as well, and I think it helps you here from this navigator. You can launch a new environment. You can use Jupyter Notebooks here. They give you some IDEs like Spider. I found that Spider has actually been a pretty good IDE for me. It's been pretty helpful, and I think it's just overall something good you should definitely look into. Okay, so now that we, get like an idea of what these Jupyter notebooks are, so through either you can get them through Conda or Anaconda. For example, in Anaconda Navigator, you can get a Jupyter notebook. And if you don't know what a Jupyter notebook is it's this sort of open source web application that allows you to create, share code, and kind of load up normal code in this different format, an i.ip line B file. And these Jupyter Notebooks provides an environment where you can document your code, run it, look at your outcome, visualize the data, all sorts of things without leaving the environment. And each code is written in individual cells that are run separately. So if some of you guys are more new to machine learning, at least when I was new, I didn't really know exactly what Jupyter Notebooks were. I thought it had something to do with the GPU. I was a little bit confused. So when I would do my machine learning, when I would, I guess, do these machine learning competitions, I would code everything in one big Python file, just .py file, right? And that file, of course, is taking in data, training the model, running the model, giving an output, putting that to a CSV. It would do it all at once, and it would take really long. Jupyter Notebooks allow you to, I guess, split the code in a way where each cell is, I guess, you have these sort of cells that can each do their own little task. So once I load the data one time, I can use that loaded data, and I will never have to reload data ever again. I could just run the next cell, which will, for example, be training a model or things like that. So this can be really helpful, and in Python, I think, or if you're using like a terminal or something, once you install it, either you just pip install Jupyter Notebook, or use an Anaconda Navigator or Anaconda. You can just type in like Jupyter Notebook in your terminal and open up this thing in your web browser, and it really helps visualize things. This is an example at the very top of like a normal, just like pandas data frame that you'd see, when you're coding, and just like any IDE with a .py file. And in the bottom here is the kind of another chart or something that you'd see in a Jupyter notebook. A little bit easier to visualize, and this really helps in the long run when turning with more than just data sets that we're looking at. Okay, so now we kind of got an understanding of Jupyter notebooks or so. So we can move on to data preprocessing. So one of the first steps when you get your data in a machine learning problem or so is to work with the pre-processing. So there's different things you have to do. First off, you'd want to handle all the null values. I know this was one of the issues in one of the previous competitions, like the Titanic one, where you'd often get lots of NA values, NaN, none, something like that. And some ways to solve this in real life machine learning is using something like df.isNull, which would output this Boolean matrix that would show all the values that are NaN, and it would show kind of which ones aren't. And based on that, if you want to make a new data frame that doesn't have these null values or null rows, something like that, you can just do df.dropNa. And this would really help, this reduces all the null values. Another approach, though, if for example you have lots of null values and you don't want to remove this much data, or you just think that you'd perhaps rather just use an imputation method, which would be processing, or which would just be substituting the missing values of the data set with, for example, like the mean of the data set. So say I have like a list, say in this previous problem, serving size, calories, fat, things like that. And say I have like later on, right here with this Stonyfield yogurt, I had an NA for calories, something like that. I could maybe just take the average of this entire calories row and just put it in that value, just so our model could possibly still learn from, serving size, fat, saturated fat, cholesterol of this type of yogurt, but it wouldn't really get thrown off completely. Of course, this could harm the model in this case because Stonyfield has actually a really abnormal amount of calories in this case, right? And this might be something that's indicative of something not being Greek yogurt versus being Greek yogurt. So, but like that's why maybe some people would choose to perhaps just remove it entirely from the data. But in the end, it's basically up to you. Do you want to substitute these missing values in the data set with some sort of method? For example, this scikit-learn.impute simple imputer function, or do you want to just remove all these null values altogether? One more thing in data pre-processing is standardization. So what this means is that when we see this kind of list of data here with country, age, salary, and we're looking for this output, did this person or so purchase whatever product we're looking at? Yes or no? Right? We have this data, and I think at first, I mean, it might seem like this is good enough to kind of put in your machine learning model and see what your output is, right? A lot of the times when you transform these values or so, it's really difficult to compare or your model to kind of understand when you have ages, ranging from, 0 years old to 100 years old, and then you have salaries that are in the tens of thousands or hundreds of thousands, right? So since it's really hard to compare these values, if you use some sort of standardization techniques or scaling techniques, all these age values or so would be in some sort of would be like kind of scaled down so that the mean is 0 and the standard deviation is 1, and then the model has it a little bit easier to compare across all the features. And one really easy way in Python to do this is just importing scikit-learn.preprocessing and using the standard scalar function. And all you have to do is just say your new data is standard scalar dot fit underscore transform, and then you put in whatever data you'd like to transform. There's a lot of other approaches as well. There's a scikit-learn scalar method, but this method helps make the mean 0 and the standard deviation 1. So you could definitely mess around with that. And these are kind of just small things that can really help your model perform a little bit better in the end. Once we get into convolutional neural networks or CNNs, where you're taking images as your values and you're taking in, pixels from 0 to 255, then another technique would be to divide all the pixels by 255. And this way, you would kind of, by just doing this division, you would be making all the values go somewhere from 0 to 1 of all the pixels. Okay, so now that we've kind of got an idea of data preprocessing, we could talk a little bit more about the main Python libraries or frameworks that we use for machine learning. So first we have scikit-learn. Scikit-learn is one of, I guess, a more introductory machine learning libraries that you use for a lot of basic unsupervised, supervised learning. There's some examples here with regression, linear regression, things like that. KNNs, model selection. It helps with a lot of things like pre-processing, like we were just showing here. These are all from scikit-learn, where you're getting these scalars. Here we got this imputation method from scikit-learn. And essentially, I mean, it really helps in this type of area. If you guys have done the competitions and all, there's scikit-learn methods for SVMs, decision trees, random forests, things like that. And it's just really helpful in that sense. And basically, to kind of take you through a little step by step of how scikit-learn kind of works, or how you would code a machine learning model using scikit-learn, just a really basic one, would be, I guess, so say you have this training data here. You have your X and Y, and on your own, you'd like to test, for example, your model's accuracy. You're going to make your own testing data, just test it by yourself, see what happens, right? Then you would want to go through this approach. So first, you would kind of split this data into an X train, X test, Y train, Y test. We kind of talked about that, where you have your training data and your testing data. Then with scikit-learn, it's as simple as literally just saying, model equals svm.stc and just model.fit. Put in your data. Once you get your model kind of trained, you can make predictions, and based on that, you can determine the accuracy on your testing data. So this is really simple. There's of course other approaches to help improve your model's accuracy and new parameters to put in, things like that. But this is, I guess, the general idea of how you would train a model if you'd like to test your accuracy on your own. Now, if you're, for example, doing a Kaggle competition for a machine learning club, right? And you don't want to you don't want your final output to just be the accuracy on your little subset of testing data. You want to use all the data you have, your training data, and based on that, you're gonna just make a CSV file of just outputs that you're gonna submit to Kaggle. In that case, all you'd have to do is just, for example, in this case with the Titanic data, you just transform your X train, your Y train. You got your two X train and Y trains, and you just make your X tests, whatever the testing file is directly from Kaggle, and then you'd put it in the model.fit, and in the end you take your results and you export to a CSV. I'll actually talk about the results a little bit later for those cases. But essentially, these are kind of the two cases you can go through. So that was, I guess, an example of a normal, I guess, scikit-learn experience or model. Now we're going to show a little bit more about Keras, which is one of the more common deep learning frameworks, and it uses TensorFlow backend. So Keras you'll see a lot with deep learning, neural networks, CNNs, things like that. And essentially, they work very basically. So besides the kind of test train split or the pre-processing like we were doing here, where you're getting your X train and Y train and your testing data ready to put into that model. All you have to do, I guess, with Keras or so, this is an example of how you'd use Keras for a neural network. So I guess before, like we've learned about these neural networks as we have these input layers, hidden layers. Eventually, you get to your output layers. You have all these kind of nodes throughout your network, right? In Keras, these nodes are just defined as adding these dense layers. So each of these would be considered like a dense layer, and in each dense layer, you have you can specify how many of these nodes would you like. In this case, it's 3, 4, 4, and one final output node. In our case, you could say you could put in your input data, get 256 nodes, then feed that into another layer with 128 nodes, so forth. In the end, you get one last node, and this would be, for example, if you're doing a binary classification problem on does this, you know, does this patient survive or not for the Titanic data set? Yes or no. You'd want to use one output neuron or so with the sigmoid activation function or something like that, and use some sort of binary cross entropy. And this is kind of just the model itself. This is all you really have to do to make the model. You define the sequential layers, you add the layers in, you compile it using your loss function, which in this case would be binary cross entropy because we have two classes, and you define what are your metrics. If we're using a classification problem, you would use accuracy, and in other cases, you could use different things if you're going with a regression problem. But then all you'd really have to do is the next phase would just be model.fit x train, y train, and here you'd be typing the number of epochs, or epochs would kind of be the number of iterations your model goes through completing this x train, y train, and your model kind of learning from it. And each, as you can see here, like in each epoch, the model is increasing in accuracy just a little bit. But I think a lot of the times, at first, this might seem like, my model is improving more and more each epoch. I should increase the epochs to 100, right? But the issue with this happens is that when you keep training your model over and over and over, as we discussed in the neural network videos, this will lead to things like overfitting, your model kind of almost memorizing the data and things like that. So here's where you kind of mess around with the different parameters, different number of neurons, how many epochs, changing the batch size, which is like how many items or so get passed each time, and things like that. So now is the more difficult part, I guess, of when you have any machine learning problem, which is hyperparameter tuning. So a lot of the times, if you guys have done the previous competitions, the SVMs, decision tree, or you're trying the neural networks and things like that, tuning these hyperparameters can a lot of the times just be things like guess and check, right? I have my SVM. You think about what method, what functions you're gonna put in, what values for gamma and c and things like that. Or in the case of neural networks, how many layers am I going to add, how many epochs, things like that. So actually, one thing that is really helpful is scikit-learn has their own little guess and check processes called grid search and random search, and they help with things like SVMs. And essentially now, instead of having to put my own, gamma values, C values, things like that, I'll just kind of give my grid search or so like a couple of options on things to choose on, and grid search will automatically give me the values I need that would give my model the highest accuracy or so on the testing data. And this way you can kind of just run this grid search thing, which might take a long time, but once you figure that out, all you have to do is now you don't have to, mess around with different hyperparameters, try new ones. You take the output that grid search gives you and you put it in your model, and then you're basically done in that sense. So this can be really helpful. Okay, so once you kind of reach the stage of a machine learning problem where you've, gone through the data, you've gone through, fit your data, you've made your predictions, right? And say this is on your own testing data. So I took, like in the previous example, right here, I took my data, my X and Y for my own use, I split it into training and testing, I fit it, I made predictions, and I found my accuracy in the end, right? I was trying to get the highest accuracy. This isn't like anything I'm submitting to Kaggle. I'm on my own, making my own testing data and finding my accuracy. So a lot of the times, the best way to kind of figure out how accurate my model is to kind of use a confusion matrix. And what this confusion matrix is it shows exactly what your model's predicting and like how. So it'll show, for example, in this case, if you have 165 testing data, values or so, and you're predicting yes, the person survives Titanic, no, the person doesn't survive, right? Before, if you just look at the accuracy here, it seems pretty high and all, but a lot of the times your accuracy itself can be misleading. So it's important to use a classification or confusion matrix to determine how accurate it is at, predicting real yeses or real nos or things like that. So this case will be like looking at a classification matrix. Here we have 55 predicted nos, right? And out of those 55, 50 were actual nos. Similar with the yes category, we have 110 predicted yeses and 100 were accurate yeses. This is kind of how you read this confusion matrix. So in total, it made 50 plus 100, 150 accurate predictions, and then these 15 predictions were incorrect because our model, here it predicted no, and the actual was a yes. And in this case, we predicted yes, but the actual was a no. So there's proper terminology for this. They're called true positives and true negatives in the cases where a model is correct. So these 100 would be true positives, these 50 would be true negatives. And then a false positive is when our predicted value is yes, but the actual value is no. So here would be, our predicted value is yes, our actual value is no, and a false negative would be the opposite. So our predicted value is no, but the actual value is yes. So kind of a little bit confusing if you think about it, but it does make sense. A false negative, your model was it predicted no while the answer was yes. So it's giving you negative for, I guess, no reason or so. So what you kind of want to do with these confusion matrices is determine the precision and recall. So what precision is precision essentially asking this question: what proportion of our positive identifications were really correct? So for example, the formula I guess would just be you take your true positives and divide that by the true positives plus the false positives. So in this case, it would be our true positives would be 100, and then true positives plus false positives is 110. So our precision is 100 out of 110, which is fairly accurate. Then for recall, we would be saying what proportion of the actual positives was identified correctly. So these two questions, when you think about them like side by side, they seem pretty similar, but they're really not. This question is asking, out of all the actual positives, how many did our model identify correct? So in this case, there were actually 105 yeses, and our model predicted 100 of them accurately. So our recall would be slightly better than our precision. It would be 100 out of 105. So one thing to note is that a lot of the times, for example, if I have, my data, I have a data of Titanic, people on the Titanic, and I'm trying to predict yeses or nos, right? And say what happens is my data is naturally, 75% yeses and 25% nos. The issue here could be is I could be testing my model and it could be saying I have a 75% accuracy, and I'd be thinking that means my model is working. It has a high accuracy. But in reality, the truth could be it simply predicted every single um, image as a yes, right? And since what we said was that 75% of the values of data or the testing data was just happened to be a yes. Our model seems like it has 75% accuracy, but if you consider things like the you know the recall, the recall would be, for example, something like say there were 50 yeses, there would be zero predicted nos, and then the precision would be something, or the recall and precision or something would be very like terrible values. And in this case, it's really essential to make these confusion matrices to make sure your model is not predicting a lot more yeses than you would like, a lot more nos. Because you could have a model that's, say, 90% accurate, and you think it's probably evenly guessing yeses and nos, evenly getting them incorrect. But in reality, it could be getting all the yeses correct, and just the nos, that's where it's really struggling. And based on that, you can make adjustments to your model. So in Python itself, you can use Seaborn and Matplotlib together, like we discussed before, to make these confusion matrices. So this is an example of a confusion matrix using the MNIST data, which is like 10 digits you're predicting from. It's the current neural network competition, and here we have the not true labels and our predicted labels. So as we can see, out of like the true zeros, we got 967 out of, let's see, there were 2, 3, plus 8, 11, 12, 13, 16, 16 plus 9, 67. So we had about 983 values that were true zeros, and our model predicted 967 out of them, so that's fairly accurate. And if you do a similar thing throughout all the values, for example, our true ones and our predicted ones was really high value, and we can see that there's not really any noticeable issues here with our model. Perhaps the largest number here is a 9, and we could think about, why is it getting 9, why is it predicting a lot of these 9s as 3s? And we could think, okay, yeah, 3s and 9s are, fairly similar numbers. That could be the reason when we write them out. Or there could be some other issues that we might have to, fix with our model. But these confusion matrices can help visualize the model and make sure that there's nothing kind of wrong happening. Okay, so moving on to, I guess, if you were doing the actual neural network competition or the decision tree random forest competition that we actually have at the TJ Machine Learning Club, we want to get our output in some sort of CSV file, right? So after we do this, model.fit stage, or as we were down here, this model.predict stage, there is no accuracy score we're doing. We don't have the testing data answers, right? All we have is an X train and a Y train training data, and we have the testing data of the X's, but we don't have the Y's, right? We don't have Y tests. We only have X tests. We need to make a data table or a CSV file of all of our Y tests that our model predicts, and then Kaggle will score that for us. So in that case, what we want to do is we want to we can use like pandas and NumPy or so, and it's really easy if, for example, if you just use something like np.reshape or concatenate to merge your final Y prediction array with just an ID row, that goes from 0, 1, 2, 3, 4, and so forth all the way down. All you have to do to write the CSV file is just make a pandas.data frame, specify what the column names are, and just add your data that most likely already has these two columns that you made. And this way you just make your out file an out.cs2 CSV. If some of you guys were in our previous competitions, taking your data, putting it in an Excel file, manually adding the ID solution, manually adding all the rows, you could try using this method instead. It's a lot, quicker, a lot more efficient, and this will help you out in the long run. But this is kind of all you'd have to do. Pandas and NumPy really help you out here and make it really easy to make these CSV files and easily accessible. Yeah, so portions of this lecture have been adapted from Kevin Fu's last year's October 2019 Real World Machine Learning lecture. I made some slight adjustments and posted that on the website actually today. So if you want to check out the lecture as well, you definitely can, because it has a little bit more of like the code I was adding here that you could, if you'd like to use that code or I guess mess around with it or see the code in, I guess, one place together, you could definitely check out the lecture. And at the very end, there's a lot of different resources you could use to learn more about using Keras, scikit-learn, things like that, or just get a little bit more informed. But yeah, that's pretty much all we have for the real world lecture. So I guess just a quick the overview is we went over how to first pre-process the data, moving on to scikit-learn models, Keras models, how would you tune hyperparameters, talking about what does your output mean, what do your final accuracies mean, and can they give you some false hope that you think your model is 75% accurate when in reality all it's doing is predicting yeses on an imbalanced data set, right? So I hope you guys learned something and you can kind of use this. And just to let you guys know, definitely try to work on the uh, neural network competition or so, even on your own time. That competition should be done by hand, and it would be definitely interesting to try that. And once the competition's over, you could try Keras and NumPy and see how your handwritten model, your neural network compared to Keras's models. And yeah, see you guys next time.